When a proprietary large language model is deployed through a public API, the core intellectual property of the developer is exposed to the open web. If an adversary can replicate the model's behavior through that endpoint, the service provider's commercial advantage evaporates. To maintain traceability, providers use watermarking. They embed a subtle statistical ripple into generated text, a mathematical signature identifying stolen content. Within the industry, there is a common assumption that these cryptographic markers provide a robust safeguard against theft. But a research paper titled Delta Steel challenges the reliability of that protection. In testing, researchers were able to bypass proprietary watermarker detectors with a success rate of 96.95%. They achieved this result without compromising the functional intelligence or utility of the replica model. The Delta Steel results indicate that internal watermarks are susceptible to post-extraction manipulation. This vulnerability suggests effective protection requires moving beyond the model's internal data and toward a broader behavioral defense. In a typical session, a legitimate user queries the model and receives a high-quality response tailored to their prompt. An attacker replaces the user with an automated loop. A script sends a continuous stream of queries to the same API to observe how the model responds to a massive variety of inputs. This process generates thousands of specific input-output training pairs. By scraping these interactions, the adversary builds a dataset that maps the target model's internal logic. The attacker then uses these captured pairs to train their own surrogate model offline, tuning it until its behavior matches the target.
Because the surrogate is trained directly on the original model's outputs, the frequency pattern of the watermark typically transfers into the replica's weights. Usually, this is how a provider proves theft. They query the replica, find their proprietary watermark, and confirm their data was used. The critical threat, however, is not just the extraction of data. It is the attacker's ability to mathematically sever that link of traceability before the replica is ever deployed. The Delta Steel attack intervenes at the moment the adversary is fine-tuning their surrogate model. During this phase, the attacker injects local differential privacy, or LDP, noise directly into the surrogate's token embeddings. In this context, LDP noise is a calculated layer of static. It is designed to obfuscate the specific statistical signals that the provider's watermark detectors search for. This targeted noise successfully masks the watermark signature, all while leaving the underlying semantic structure of the model completely intact. Once the signal is obfuscated, the original service provider has no mathematical basis to claim that their data was used to train the surrogate. The success of the attack depends on balancing the LDP noise hail. As the chart shows, too much noise will destroy the watermark, but it will also degrade the model's intelligence. An adversary seeks the precise intersection where the noise is strong enough to hide the watermark, yet light enough to keep the model useful. Because post-extraction manipulation can effectively strip the watermark, security efforts must focus on preventing the initial extraction of training pairs at the API perimeter. Inference time attacks encompass more than just model extraction. They all exploit the inherent statistical flexibility of neural networks. For example, evasion attacks involve crafting specific inputs designed to trick the model into making a predictably wrong decision. Attackers often use the concept of transferability, optimizing their evasion prompts on an offline surrogate model before launching the finalized attack at the real zero-knowledge target. Prompt injection also leverages this flexibility, but it differs from strict vulnerabilities like SQL injection. A database follows a rigid schema. An LLM interprets natural language, which makes it difficult to differentiate between data and instructions. Direct prompt injection aims to jailbreak a model's safety alignment through dialogue. Indirect prompt injection is more subtle. In an indirect attack, the malicious instructions are hidden within external data, like a web page or a file, that the model reads while performing a task, such as summarizing a link. These methods highlight a core challenge. It's incredibly difficult to build safety alignment that consistently distinguishes between information to process and commands to follow. To manage these risks, engineers look to the OWASP framework's 7 layers of protection. The objective is blast radius control, architecting the system so that even if a malicious prompt reaches the model, the damage is strictly limited. One essential layer is the implementation of obscured confidence. To optimize attacks, adversaries need high-precision confidence scores, the specific probabilities for each token. We intentionally truncate and round these scores. Rounding these values denies the attacker the high-fidelity signal they need to calculate the mathematical gradients required for extraction or evasion. The second architectural pillar is unwanted input series handling. Most inference attacks rely on iterative probing, where the attacker sends many slightly different prompts to see how the output changes. By monitoring for statistical similarity and optimization patterns across a sequence of inputs, we can identify and block an attack in progress. These defenses are anchored by infrastructure-level controls, strict rate limiting, and model access control. When combined, these measures shift the timeline for a successful model extraction from minutes to weeks. This creates a window of time where anomaly detection can identify the pattern and disable the account before the IP is lost. The Delta Steel research demonstrates that once a model's outputs are extracted, internal trackers cannot be relied upon to prove ownership. Local differential privacy noise provides a reliable mathematical way to strip away watermarks while preserving the model's value. This forces the security perimeter for production AI outward. Protection must happen at the point of interaction, rather than within the model's weights. For security teams, this means moving away from the goal of creating an inherently untrickable model. The solution lies in building environments that detect, obscure, and throttle the high-precision telemetry that all inference time attacks rely on to succeed.